All right, so today here in section 6.3, we continue on with our studies of inequalities, that is, proof theorems that all say when something, a segment triangle, is greater than another. And in this section, we do extend beyond just the relationships inside a single triangle and instead consider relationships between pairs of triangles. And what we'll get today is very much an extension of side-angle-side congruence and side-side-side congruence in the same kind of way that the anisosceles triangle theorem was an extension of the isosceles triangle theorem, and the converse of it was an extension of the converse of the isosceles triangle theorem. So let's get to it. So the Hinge theorem, the first of the two results that we'll prove today, the Hinge theorem says this. Let us say that we have two triangles with two sides of one equal to two sides of the other, and the included angle of one greater than the included angle of the other. So not side-angle-side congruence, though like it in a way, both here and in side-angle-side, we have to have two sides of one equal to two sides of the other. But now we say that the included angle in one of the triangles is greater than the included angle of the other. Now what the Hinge theorem says is that in this case, the third side of the triangle with the greater included angle is the greater of the third sides. And it should be clear why this theorem is sometimes called the side-angle-side triangle inequality, because we do have that kind of side-angle-side pattern, right? We have two sides of one equal to two sides of the other. But the A in this case signifies that the included angle in one is greater than the included angle in the other. So the greater opposite side, opposite the included angle, will be the one that is opposite the greater angle. All right, so here's a picture of this. So we have two triangles, ABC and RST. And as you see, we do have like the precondition for the Hinge theorem. We have two sides of one equal to two sides of the other, namely AB is equal to RS and AC is equal to RT. But now notice that we say the included angle in RST, that is angle R, is greater than the included angle in ABC, that is angle A. And then we conclude that the side opposite the greater included angle, that is ST, is greater than the side opposite the smaller included angle, that is BC. Now, as for how this gets proven, it will be simpler if we have a lemma in place. We've encountered this language of lemma before. A lemma is just a theorem, okay? But the reason we call a lemma is that it signifies its position in the order of theorems. It's like a helper theorem. Usually not difficult to prove, not always true, but in this case, not difficult to prove. And then once this lemma is in place, we can call upon it in the proof of a later theorem of for us, the theorem of real significance. Lemmas help to organize our proofs. It means that we don't have to put so much into one particular proof. So let's prove this lemma H. I call it H because it's a lemma to help us with the Hinge theorem. And here's what it says. It says that the angles under the base of an isosceles triangle are obtuse. And of course, you'll like to know what I mean by under the base. So here it is. So we have triangle ABC with AB is equal to BC. So this is isosceles. And then what we've done is this, is we have extended the legs so as to create angles 1 and 2 as shown in the diagram, which is what I mean by the angles under the base. And those two angles must be obtuse. And how does one prove this? Well, it's not particularly difficult. Consider the angles with which they form linear pairs, perhaps 3 and 4 in our diagram. So 3 and 4 in our diagram. So 1 forms a linear pair with 3 and 2 forms a linear pair with 4. So let us ask about 3 and 4. Could they be, they have to be equal of course, but could they be either right or obtuse? Well, if 3 and 4 were both right, then, well, of course, AB and BC would be parallel, which they're not. Also, when we add in the measure of angle B, we would exceed 180 degrees, so 3 and 4 cannot be right. And for the same reason, 3 and 4 cannot both be obtuse. If both 3 and 4 were obtuse, then the sum of the angles in triangle ABC would certainly exceed 180 degrees. So 3 and 4 cannot be right, they cannot be obtuse, so they must be acute. So 1 forms a linear pair with an acute angle, and 2 forms a linear pair with an acute angle. And of course, linear pairs are supplementary, so it follows then that angles 1 and 2 have to be obtuse. So remember that. Now, here's the proof of the Hinge theorem, which is one of the classical proofs. So we've got our two triangles ABC and RST, and it perhaps should come as no surprise that we form a construction. So the construction is this. We construct segment AZ such that, first of all, the measure of angle ZAC is equal to the measure of angle SRT. Okay, so perhaps indicate that in the diagram with a bit of color coding. So first of all, AZ has been constructed such that the angle ZAC is equal to the angle SRT. Those must be equal to one another. And if you like, what we've done initially is we've constructed an array through A and a point Z such that the angle ZAC is equal to the angle SRT. And then we mark the point on that ray such that A to that point, which I've called Z, is equal to RS. So it's like two construction steps together. Construct a ray to give us an angle of a certain measure, and then on that ray, pick out a segment of a certain length. Okay, so this is what we get, as you see in the diagram. And we wish to prove, of course, that ST is greater than BC. But notice this, okay? Notice that just given the constructions that we have done, that triangle ZAC is congruent to triangle SRT by SSS congruence. And so it follows, of course, that ZC must be equal to, need 3 hash marks, that ZC must be equal to ST. Okay, so we've kind of transferred the length of ST over to a diagram that includes the original triangle ABC, and it's been transferred as ZC. Okay, so what we really mean to prove then is that in triangle ZBC, you see that little sort of side triangle ZBC, that in that triangle, side ZC is greater than side BC. And this is really the significance of this proof, okay? We start off initially with two distinct triangles, right? And it would be far from clear how it is that we could use any of the previous results that we have proven because they all concern what happens inside of a single triangle. But now we've like transferred one of our original links over so that it now is together in a triangle with the length to which we were supposed to compare, right? So it becomes at least possible in principle to use something like, I don't know, the anisosceles triangle theorem. So that's really the goal here, right, is to do work inside of triangles EBC. And the idea is this, is let us extend AB through B in a straight line path, and then consider the angle that gets formed. Now, it might be a bit difficult to see this. Say I have a point on that extension that I'm going to call, I don't think I've used D yet. So the extension of AB we'll call BD, and then consider that angle number 1 that gets formed, which is angle ZBD. Apply lemma H, okay? By lemma H, that must be an obtuse angle, and then consider the relationship of angle ZBC to ZBD. ZBD is just part of ZBC, which means that ZBC is greater than an obtuse angle, which means that angle ZBC is obtuse. Okay, certainly looks it, but we can prove it. Angle ZBC must be obtuse, which means that angle ZBC is the greatest angle in triangle ZBC, which means the side opposite is the greatest side. That's the converse of the anisosceles triangle theorem. So it follows in particular that ZC must be greater than BC, which is what we wish to prove. All right, now converse hinge, should be no real surprise what this is. It's like sort of the extension of SSS in the way that the hinge theorem itself was an extension of SAS congruence. So it says this, let us say that we have two sides of one triangle equal to two sides of a second triangle, but the third side in one is greater than the third side in the other. That will be the one that has the greater included angle. Okay, so if we compare the two triangles and we look, and the precondition is met, that is two sides of one are equal to two sides of the other. If we look in the triangle with the greater third side at its opposite angle and compare that to the opposite angle, the smaller third side in the other, the angle opposite the greater third side is the greater angle. So it is precisely the converse. So here's what it looks like. So we have the precondition for converse hinge, which is that we have two sides of one triangle equal to two sides of the other, namely AB is equal to RS and AC is equal to RT. And then we say, as the final part of the given, that the third side of RST, that is ST, is greater than the third side of ABC, that is BC. And then we wish to prove that the angle opposite ST, which is angle R, is greater than the angle opposite BC, which is angle A. And then as for how this gets proven, well, it gets proven indirectly. So let us assume that angle R is not greater than angle A, okay? That angle R is not greater than angle A. And then think about what the two possibilities would be. And this is very much like the proof of the converse of the anisosceles triangle theorem. If angle A is not greater than angle A, it's either equal to or less than. Okay? So think about that first possibility, that angle R is equal to angle A. It would then follow that triangle ABC is congruent to triangle RST by SAS congruence. And then from that, by CPCTE, it would follow that BC is equal to ST, which contradicts the given. We know that ST is greater than BC. Likewise, if angle R were less than angle A, which is the second possibility, then we could apply the Hinge theorem. The precondition for Hinge is met. We have two sides of one equal to two sides of the other. So if angle R was less than angle A, it would follow that ST is less than BC, which again contradicts the given. So we could rule out both possibilities, which means the original assumption must be false. It's false that R is not greater than A, so R is greater than A. So there it is, Hinge and converse Hinge.